My neuropathology exam indicates that our victim succumbed to a cerebral embolism here in the parietal lobe. I also found a number of clots, most of them centered in the renal artery.
Isn't that unusual?
Oh, not at all. In most cases of arterial thrombosis, clots will develop over a period of minutes or hours, spread to the rest of the body.
But what caused them to develop in a healthy young aviator?
Abby?
Well, I did a fibrinogen test. The procoagulant numbers were high, but they weren't off the charts.
Wait, fibrino what?
Well, let me explain.
First, let me talk about the molecules that cause the formation of a blood clot, called clotting factors. Clotting factors are enzymatic proteins that interact with one another in what's called a clotting cascade, which is basically the biochemical pathway that causes a blood clot to form. When these clotting factors are circulating in the body's blood normally, they're in a form known as zymogen, which is the enzyme's inactive form that is typically altered through interaction with another molecule to become active. Another name for clotting factors is procoagulants because they promote coagulation. Most procoagulants are produced by the liver. Those that aren't undergo a post-translational modification. Now, here's a quick refresher on what that means. Translation is the second major step in the process of creating a protein from a DNA, in which the end product is the protein. A post-translational modification, as you can guess by its name, occurs after the protein has been translated. In the case of the clotting factors not produced by the liver, vitamin K is utilized to carboxylate, which means to add a carboxyl group, usually in the form of carbon dioxide, to the glutamic acid residues of the protein. This modification allows the molecules to bind to other molecules in the pathway. Going back to our clotting factors. To answer your question, Tony, fibrinogen is a glycoprotein, a protein with an attached carbohydrate molecule, that is the precursor to fibrin, which is an insoluble protein that cross-links to help form a blood clot. We'll talk more about that a little later. A fibrinogen test measures the level of fibrinogen in the blood. Too low numbers can be bad for the body because any kind of vascular damage might not be completely fixed by a clot, or it might take a while for a clot to form, meaning a larger amount of blood will be lost for a longer period of time than what's normal. However, too high numbers indicate that lots of clots will form or are forming in the body, which can cause tissues to receive limited blood supply, which is also bad. Now let me give you guys a brief overview of the clotting cascade. I'm just going to go over what is known as the common pathway, since everything else before that is mostly a bunch of clotting factors interacting and activating one another. For this, I'll bring in a little diagram I drew up. Keep in mind that a factor name written with a lowercase letter A after it means that the factor is in its active form. The key to the start of the common pathway is the activation of factor 10. Once activated, factor 10 binds to factor 2, which is prothrombin, and activates it to make factor 2A thrombin. This initial thrombin activation isn't enough to generate the whole cascade, so, in a positive feedback loop, in which increasing amounts of a molecule in the body increases the body's response to the molecule, thrombin binds to blood platelets, which causes increased thrombin production. Once enough thrombin is generated, it is able to interact with two other clotting factors, fibrinogen, which is altered into fibrin through the binding of thrombin, and fibrin stabilizing factor, also known as factor 13, which then cross-links fibrin molecules into a stirring network. This fibrin network then joins with platelets to form a blood clot. And that's how clots form in your body.
Oh, I get it.
All right.